dealing with the cables, because today I'm kind of tethered, and this is basically as far as I can walk before the kind of long USB cable runs out of length. All right. And if this works out well, I'm going to ask the school to pay for one. All right. So what we'll do today is to take a look at the practice test. I forgot one or two questions on double, in the practice test. So we'll go ahead and add one when we get there. I will share that document with you guys, sometime during the class. Okay, this is cisp310. All right, so what we are seeing here is the actual exam from last semester. Most of this is going to be the same. I still want you guys to write your last name, which is your family, also known as surname first, okay, and then followed by your given name and your student ID. And please try to use your best penmanship, at least with this part, because a lot of times I cannot read the entire name correctly, so that makes it kind of difficult for me to match the grade sheet with the score of an exam. The time obviously is not going to be the same, different date. It's going to be next Thursday, so it's 1 week from today. That would be our test. Room number changed, but it is still going to be open book and open notes. So anything that is written or printed prior to the test, you can bring. Are there any questions about that part? No questions? Yep. 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 You can print my notes. I mean, just go ahead and go to Canvas, print out every single PDF there is. If you go online and you say, okay, I found a better description of carry look ahead, adder, which there are plenty of. You can print those out too. You can manually prepare a quote unquote cheat sheet to summarize everything, so it's easier to locate the information. That works too. Or if you look at watch my video and say, okay, that particular screen is really helpful, take a screenshot of that, include it and print it out, bring it with you. That's okay too. So anything that is handwritten or printed prior to the test is okay. Okay, you can bring in books, you can bring in your assignments. Okay, so your 3-bit adder, if you want to bring that, print it out and bring it with you, that's fine, not a problem. Okay, so at the same time, okay, if you look at it in the opposite direction, at the same time, I'm assuming that you guys know this already, that it's open book and open notes, and you would bring everything that will help you with the exam. Okay, so it is your responsibility now to figure out, okay, what do I want to bring with me? How do I want to index the material that I'm bringing? Because just because you have all the material available doesn't mean you can locate the proper page or the proper diagram quickly. So it's up to you to decide what is the best way for me to index everything. Is that okay? All right, okay. This is an individual assessment, so I really will emphasize on, making sure that each submission is only reflecting the performance of the students who's turning in the test and not anyone else. You can use additional sheets of paper. I will give you space on the exam paper itself to write your answer. But occasionally, some people would say, okay, I want to scratch the entire thing, then you'll be out of space. So my recommendation is to bring binder paper, or just any paper is fine, okay, as long as it's about the same size as letter size paper is good. But you might want to bring like a stack of paper with you, just in case you run out of space to write something. Then you don't have to scramble and ask for someone to give you a piece of paper. Is that okay? All right. Definitely you want to write legibly, because if I cannot decipher your answer, okay, I cannot give you the points. So that's the bottom line. Questions do not have equal weight. In other words, some questions carry more weight, other questions carry less weight. My recommendation is to take a quick scan of all the questions, okay? And then you say, oh, this one is easy. I know the answer right away. Okay, that one is easy. Work on the easier ones first. Even if they are lower point value, work on those first. Because that way you lock down the points that you can get for sure early on in the exam. If you spend a lot of time on the hard questions that might carry more weight, you might run out of time to work on the ones that are really easy. So, so the idea is you want to lock down all the points that you can get easily first, and then you go back and work on the harder ones. That's my recommendation. I will tell you the number of total number of questions. It may or may not be 6. Okay, but this is just kind of the way I think. Okay, maybe 6. The exam accounts for 20% of your final grade, which means if you score 100% in this particular test, it will add to up to 20% of in the end of the final total. Is that okay? So can someone remind me, what is the percentage that you need at the end of the semester to pass this class with a C? 37.5%, exactly. So, so keep that in mind, okay? Keep that in mind. All right, so let's move on to the questions. This one needs to be crossed out because I said that your memory devices will not be in this particular exam. So, forget about question number 1. I will share the link to this document. So we'll just go ahead and strike through this one. Okay, and strike through question number 2. Oh, that doesn't leave a whole lot of questions here. But this one we can keep, okay, because this one has to do with adding. So the question says, in binary subtraction, the result function R is basically x and not y, or not x and y. We know that already. It's the same thing as x exclusive or y, xy being bits. And the borrow function is wrong, okay? The borrow function is supposed to be not xy, not x and y. No idea why I got it wrong here. In the carry look-ahead subtractor or borrow look-ahead subtractor, the bit bi, the borrow bit bi, can be recursively defined as this. Have we seen this somewhere before? Let me magnify a little bit because it may be a little hard for you guys to read. Have we seen this before? Yep. In fact, we have seen the pattern twice. Once when we were dealing with adders, and the second time is when we were dealing with subtractors. Okay? So part A is asking, what are the terms GI and PI? So how do we define GI and PI to make this recursive definition work? What do you think? Okay, go ahead. Do you guys remember the definitions of GI and PI? Yep, so in this case, okay, so I'm going to put the answer here. Let me share this first, okay? Because for those of you who have a computer and you say, okay, I want to look at this from a computer, you can do that. So I'm gonna say advanced and change this so that everyone on the web can find it and everybody can view it. There we go. Click that. Copy the link, and we'll go to Canvas and link it to one of the announcements. I'll put it into an announcement. And this is the Tuesday, Thursday class. And I'll just put the link here. we go. So now, if you have a device with you, tablet, phone, or whatever, you should be able to actually see the document as I edit the document and insert the answers. All right, so in this case, G subscript I is defined to be, is defined to be the negation of xi and yi. Do you guys remember this? Okay.
Same as the borrow function?
Yes, it is the same as the borrow function itself. Yep. And then what about the P? Yep. So PI is not XI or YI. Is that right? Okay. If you remember, the way we worked on the subtractor is, we just needed to add a negation to the gates that will generate the P terms and also the gates that will generate the P terms. Everything else stayed exactly the same. Okay, and that's basically what it is. Okay, part B, using the recursive definition, derive and spell out B2 step by step by expanding the BI terms one step at a time. So what I mean by this is to start with the actual definition, which is given here. So, so B2 by definition is G1 plus P1 B1. Okay, so now you need to expand B1. So this now becomes G1 or P1, but then you expand B1. B1 is substituting 1 here. So that itself becomes G0 or P0 and then B0. Is that okay? All right. So when you use distribution, then you end up with G1 or, and then you distribute the P1 over the disjunction in the inside. So you end up with G0 P1 or P0 P1 and B0. That's the answer that I'm expecting. But not just the final form, but also the intermediate equations, so I can see how you expand it one step at a time, and each time you're using the definition, which is up here. Is that okay? All right. Moving on to part C. Part C asks, assuming that we only have AND and OR gates and have 2 inputs, and each gate only has 2 inputs, how many gates in total do we need to compute B2? Derive your answer step by step and explain the rationale. In other words, looking at this, okay, because I'm only interested in B2, I'm not interested in the difference in the subtractor, just B2, so our focus is just that part. So the question is, how many AND OR gates do we need? And each one is confined to only have 2 inputs. Okay, so the way you work on this is you work on it from the bottom up, okay? So if I were to do this, I can do something like this. Okay, so I can say, okay, so I'll define each term, and each term is only going to involve a 2 input gate. Yep.
Does that exclude negation? Or
we don't need negation.
you don't need, okay.
Because we already, well, okay. So my original question is, given the P's and the G's, okay, how are you going to do this?
Gotcha.
On the other hand, if you want to include the actual generation of the P and the G terms, that's fine too. So I would accept both as correct answers, as long as they're consistent. so you're right. Okay, so if you want to start, because the question is ambiguous. It didn't say do we start with the p and the g's already given, or are we starting with only the x and the y's? Okay, so you can derive it one way or another, making one assumption. Okay, so let's go ahead and use the other one. Use the second one, which means we are starting with g1 is not the negation. You can put it. It can associate it with the AND gate here, because remember we can put a bubble on an AND gate to negate one of the inputs. So you can make an assumption that we can do that here. So this is x1, y1, g0. Now, you just need to have the rationale explained. So whether you spell out every single term, that may not be necessary. So P1 is not x0 or, oops, not x0 or y0, well, y1. Yep. And then P0 is not x0 y plus y0. So here we have 1, 2, 3, 4 gates already. Okay. And then on the next line, I will have the intermediate terms. Or the other way to do this is simply to use parentheses to kind of group your operators. So this way it is clear how we're going to do this. So to do that, I'm going to cheat a little bit, because I'm just going to copy and paste this here. But this time I would use parentheses to indicate what gates we need. Between these two, here's one AND gate. The result of this AND gate will feed into another AND gate on top of this, which is represented by the second pair of parentheses, the outer pair. And then this is one pair. Okay, this is by itself one AND gate. That's cool. And then we can also have one OR gate to perform this particular disjunction. And then the entire thing is done by the other disjunction gate. So now the answer is going to be, okay, let me use the pointer here. One AND gate, two AND gates, three AND gates. Okay, so out of this line here, we have 3 and 2 gates. How about the OR gates? One OR gate, two OR gates. If you want to include the P's and the G's, then we have 2 and 2 gates, and then 2 OR 2 gates. So the total is going to be, depending on which assumption you use, so the total is either 5 or 9. Unless I do some really bad mistake doing arithmetics. Is that okay? Making any sense? Okay. And that's the end of that question. And the rest are, they're not, I cannot ask those questions because we haven't really talked about those yet. Question number 7, which is added, this is not a part of the exam last semester. Assuming the use of 2 input exclusive ORs, AND gates and OR gates with optionally negated inputs, what is the total number of gates what is the total number of gates to propagate through in a 3-bit carry look-ahead adder that has an overall carry bit? Show your reasoning step by step and use equations to compute the various components. So this is a different question compared to the previous one. The previous one is just asking if I were to compute B2, okay, or in your homework assignment it's called T2, how many gates do we need to compute it, but not how many levels of propagation we need to get the calculations done. This one is asking you, how many levels of propagation do we need? So one is looking at the total number of gates. The other one is looking at, okay, given this is the input, the x and the y's, and given this is the sum, and that's the overall borrow, how many gates do we have to go through to go from one end to the other end of the subtractor? Is that okay? So far so good or not? No? Yes? All right, so maybe it helps to look at a diagram. Okay, so I'll go ahead and just use a diagram to illustrate the difference between what these two questions are asking. Okay, so we are limiting ourselves to use only 2 input gates. By the way, there's a way to change the default, and I think if you just click on one without slapping it over here, and you change it here, it will change the default. So if from here on, if I only want to use 2 input AND gates, this will make sure that all the gates that you create out of this tool will be 2 inputs. And the same thing for OR. So I might want to do this so I don't have to re-specify the size of things over and over again. All right, so this is not your homework assignment. It's not related to the question that I'm asking. It's just here to illustrate the concept, okay? And I'm gonna have one OR gate over here and one more AND gate over here. Okay, and we'll have some input pins. So remember, this has nothing to do with the question itself. It is just here as an illustration. Okay, so we got this going here, this going here, and the negation is free. Okay, so we can consider negation gates to be free. So I can have one negation here and leave the other one not negated. Okay, like so. This one goes here, this one goes here, this one goes here, and we'll have this one going here. Don't ask me what this logic is going to do because it has no specific meaning. There we go. And now we have the final output pin like that. Okay. So when you look at this diagram, if I ask you how many gates total are we using, then you can just count. We got 1, 2, 3, 4, 5. So the total number of gates is 5. But if I ask you if I need to go from the input pin to the output pin, how many gates do I have to go through or propagate through? The answer is only 4. It's only 3, sorry. It's only 3 because these two are happening at the same time. So it only counts as one single level. But if you want to count all the first level gates, it would be this one, and yep, these two are the only ones, the only 2 first level gates. Because this one requires the output of the first level gate. This one requires both inputs from the first level gates. So these 2 are second level gates. This is the third level gate because this gate cannot give you the correct output until the second level gates are done with their own calculations. Is that okay? So can everybody see how the total number is 5, but in terms of the number of gates you have to propagate through, is only 3 in this case. So we do okay so far with this? All right. So with this one explained, we can now go back to the modules. And the adder one is just fine, okay? The adder or the subtractor would be the same. So we go to binary number addition. Because it is already spelled out here. This is why you might want to prepare your cheat sheet because there's a lot of stuff in between, okay? But the equation that we really want to get to is already spelled out, which is K3. This is the longest propagation. Okay, this is one of the most complex gates, but we'll also use this to figure out the overall total delay. So with K3 all by itself, how many levels of propagations are we talking about? Nope, because remember, we can only use 2 input gates. So this term here can no longer be done by one single AND gate. How many AND gates do we need to implement this? We need 3, but only 2 levels. Okay, remember we're counting levels of propagation. So what would be helpful in this case? Okay, let me use my document camera. Set it up here. What would be helpful is to draw this out as a diagram, because then you can actually physically see, how it is going to work out. Okay. Okay. All right. So we kind of have to flip-flop a little bit here. Okay, so we have P0, P1, P2, P, and then K0. We basically have 4 inputs, right? Okay. Maybe we can do it this way. I will just go ahead and okay, we can do it like that. And put this one here, put that one back on top. Okay, so I just have to slide this down a little bit like that. Okay, that works. All right. P2, P1, okay? So these two, they can go to one conjunction gate. But that one can be shared, okay? Because it can be shared between the third term and the last term, okay? So only for the last term, we need to compute P0 and K0 to take care of these two. And then P1, P2, P1, G1 can be computed as the first level too. So we're P2 and G1. So we are taking care of this. So these are all our first level AND gates. They can all happen at the same time because they don't depend on each other. Is that okay? All right. So as a second level, I can now combine P1, P2, which is computed by this gate, and P0, K0, which is computed by this term, so that we can get the last term finished. So this conjunction is computing the last term. The second last term can also be computed at this point because it involves P1, P2, and G0. So we can say, okay, here's G0, and here's another AND gate. Using the same, we are tapping out of the same output of the conjunction of P1, P2, but this time we also have a conjunction with G0. So together, this gate here is implementing the second last term, which is P2, P1, G0. Is that okay? This term is already the second term, so we have all the conjunctions done at this point. So it's time to perform the disjunctions. Now with the disjunctions, it's kind of the same deal because one disjunction can only have 2 input pins. So as a result, we have to handle this, using different levels. The first one, we can do a G2 as an input to the first OR gate. So G2 and P2, G1 can go to the same OR gate. Is that okay? So that's our first OR. And then the third term and the last term can have their own OR gate as well. So now we have another OR gate here, combining the second last term and also the last term. So first term, second term, third term, and last term. So now we have another disjunction gate overall to combine, those two. Is that okay so far? So now we have figured out the total number of propagation just to get K3 calculated. But this is not including the time that we need to generate the G2 and the P2s, the P's and the G's, but that's only one extra gate level, okay? So let's count the number of gates here, or number of levels. So we got first level, second level, third level. This is the fourth level. So this is going to involve, oops, 4 levels of gates. Are we doing okay so far with this? Okay, but this is not the answer. Okay, if you get to this part, you get partial credit because this is a key part of getting to the answer, but that's not the only, that's not the final answer. What else do we have to do? Okay, we have to +1 for computing the P's and the G's, because that's where you get the G0, all the G terms and all the P terms. Each one involves either a AND gate or a OR gate. So you need that too. What else do you need? In order to come up with a sum bit, how do we come up with a sum bit, which is what we need? Yep, so we need a result function, which is an exclusive OR. But the good thing is, this one, which is computing T or K3, is not needed for the sum. So K2 is a simpler, expression. So what do you think K2 is going to need in terms of level of gates to handle it? 4 levels or 3 levels? This is 4 levels already, but K3 is easier. I mean K2, sorry, K2 is simpler. Okay, so what we do, okay, let's take a look. This is K2. How many levels of gates do we need? We only need 3 levels. Okay, so this is 1, this is 2, and that these two can be computed at the same time. So this can be computed at the same time as first level. This can be computed as the second level. So yes, so 3 levels of gate is enough already for this one. So to get to S2, which is the sum bit, bit 2 of the sum, you need 3 levels of gates to compute K2, okay? And once you have K2, then we have the result of XY, and then the whole thing combined with K2, so X2, Y2, and then we take another result. Sorry? Is that okay? This is one level, this is another level. So we have 2 additional levels of gates once we have the K2. Now, but this can be done in parallel. Okay, so okay, let me just redraw the picture for that particular sum. We got X2, Y2, okay? We have the AND gate and also the OR gate to compute the G's and the P's, okay? So, and it's all the same for these two. And then we have that logic to compute K2, and there are 3 levels of gates here. So these go into here. Is that okay? Sort of. So K2 comes out of this. And at this point, we can pre-compute X2 exclusive OR with Y2. Okay. This is exclusive OR. So this one goes here, this one goes here. This result here is already available. So we need another exclusive OR between K2 and the exclusive OR between X2 and Y2. That becomes S2. So the question now is, how many levels are we talking about? This can be done along with the P's and the G's. This one can only be done after the P's and the G's are done. So we are talking about first level here, second, third, fourth level. This one cannot be done until K2 is done. So this is the 5th level. So it will take 5 levels of gates to compute S2, okay, which is down here. So that's the answer. This is taking more time. It's taking 1 gate propagation longer than K3. Because K3, which is in the previous slide, only takes 4 levels of propagation. Yep.
The exclusive OR is the result, right? The R.
Yes. Yep. So this is basically doing the R function. This is basically doing the R function. Because otherwise, you have 2 levels of gates to do the exclusive OR. And that's why the question explicitly allows the use of the exclusive OR gate. So do we have any questions about this part? Yep.
You wrote like the results.
Say that one more time.
So you just wrote something like the results and K, I think. Can you show that again?
The result. Okay. There's one result here. On the previous page. Okay. Yep.
So when we're answering a question like this, we just do the diagram.
Yep.
Just kind of label the levels of propagation.
Yep. That would be the best way to do it. Because one, you need a picture to kind of visualize to begin with, unless you can kind of look at the equation and be able to figure out what can occur in parallel with what else. But the picture really helps. But it also shows me that you understand how to look at this and how to analyze the level of gates. So doing it in a pictorial way is the best way to do it. Yep.
If you didn't use an exclusive OR for the result function, would it be more gates?
If you cannot use exclusive OR, then you need to add 1 more level of gates. Because the exclusive OR can be done using the exclusive OR gate by itself, or if you do not use exclusive OR, then you need the first level of AND gates and then the second level of a single OR gate to accomplish the same thing. So you have to add 1 more level of gates in that case.
Wouldn't that be running in parallel to the K calculation?
Not with the sum bit, unfortunately, because with the sum bit, it cannot occur in parallel because with this one, K2 needs to be available first before we can get to this exclusive OR. But you're converting this exclusive OR into something that looks like this. Remember, that's how it looks like a happy face. Remember, this is how we do the exclusive OR, but using 2 and 1 OR gate. But you're substituting this circuit into here. So that's why you're adding 1 level of gates overall, because there's no way to make this parallel to anything else. Okay, is that okay? No questions about this? All right. So getting back to the web's page, which is here. Back to the questions. So I didn't have time to type up Q8, and I forgot entirely that I changed the ordering of the topics this semester, because last semester I did not talk about double until much later, but this semester we talk about double first, and that's why we didn't get to some of the other questions that was on the test last semester. So with a double question, one way I can ask it is to look at a bit pattern. Okay, so I can give you a particular bit pattern. So I have to do all the mental math in my head now. Let's make it a C8, 8, and then 12 zeros. Okay. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So I would say if we know that a double has the bit pattern of this, what is the value represented? Okay. So that is probably one of the questions that I can ask. So the first thing we have to do is to convert the hexadecimal representation into a binary representation. Okay. If you want to, I can include that little table that will map a hexadecimal digit to 4 bits. Do you think you will need it, or do you think you may not need it? Yes? Okay. All right. So we'll include a table here. So this way, when I prepare the actual question, I can just copy and paste it. So insert the table. The table is going to have 18 entries. So I'll have 17 so that we can have a header. Okay. So the first one is binary. The second one in hexadecimal. So binary is easy. 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0. I should have used a spreadsheet to do this. So you might want to have a table like this handy in your own sheet as well, because otherwise you'll have to flip a lot in the exam, because all of this stuff may not be on the right page during the exam. But if you have your own, then you get to put your table on the side while you're working on the question. Okay, all right. I did not miss a single one. Okay, and let's make this look a little nicer. Okay, so in hexadecimal, we have basically the same thing: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we run out of digits in base 10. So we're going to borrow alphabets. A, B, C, D, E, F. There we go. So with this table, the conversion from this hexadecimal number into the binary bit pattern is literally just looking up, okay, what is C? C is 1, 1, 0, 0. What is 8? It's 1, 0, 0, 0. 8 is 1, 0, 0, 0. And the rest are all zeros anyways. Okay, so what we want to do is to break it up first. Okay, what is the sign bit? This is what I want you to do, is to clearly indicate what is the sign bit. What do you think? In other words, do we have a 1 as the overall sign bit? Yeah. Because the first hexadecimal digit, C, which is the most significant one, is 1100. So that means the most significant bit is a 1. Okay. What about E itself? Okay, E is biased. Okay, it has 11 bits. So the 11 bits starts with the second most significant bit of the first C, which is basically another 1, and then followed by 3 zeros. And then we have the 8 as a part of that. So this is the 8, and this is the other 8. Is that okay? All right, so what about M, the mantissa, or the fractional part of the mantissa? Oh, it is so difficult. It's complicated. Or not. They're all zeros. Very good. Okay, so the mantissa is all zeros. Like that. Okay. So what is the value represented by these particular bits? The sign bit being a 1 indicates this is a negative value. Okay, that's all it's going to say. E is a little bit tricky. We'll get back to E. But M is easy, because this M here is the fractional part of the base 2 mantissa. So what is the actual mantissa in this case? There's an implicit 1, right? There's an implicit 1 point, and then these are the rest of the fractional parts. Oh, okay, so the mantissa is really just 1 point and then a whole bunch of zeros, which is just 1, okay? Times 2 to the power of what? Okay, so I'm switching my notation here to something that I can easily type. Okay, 2 to the power not E, because this E is offset, right? It's offset by how much? 1023. Okay, so this is offset by 1023, which means we are using the power of e minus 1023. So now we have to do some base conversion. Okay, what is e in this case? This is base 2. Okay, we'll say in base 2. So if this is a base 2 number, what is the decimal number that it is representing?
1,160.
Yep, so it's 1024 plus
128.
128 plus 8. Okay, so if you use a calculator, you can just add this up to be what again?
1,160.
Okay. So once you know that, okay, I'm not gonna erase this. Instead, I'll just copy and paste it. So this number becomes 1. Oh, but we have to subtract 1023 from this too. Okay, so 1160 minus 1023 is, we got a 7 and a 3, 37, right? 137. Yep. Okay. So it's basically 2 to the power of 137. That's the negative 2 to the power of 137 is the actual value represented by a double precision floating point number that has the bit pattern that is encoded in hexadecimal as C88 and then a whole bunch of zeros. Is that okay? So this is okay as an answer. Okay, if you just tell me, the final answer is -1 times 2 to the power of 137, the way it is expressed, with all the steps expressed in between, is a good answer. Wait, do you guys trust me, and say that, yep, this is probably the right answer? No, you want to test it, right? Okay, so let's go ahead and test this. Do you remember how to test it? You write an entirely trivial program. Okay, so you go here and you cannot do it in the test, and that's the whole point of doing this on paper. Is so that you cannot do it in the test. Well, I need to make sure that my answer is correct in class. Okay, so I have to double check and make sure that it is correct. So we have, well, you can use a un64_t d, and then the return 0. And remember, we have to do something with d so that it doesn't get optimized out, because the compiler is a smartass. And the compiler will warn about d being set but not used, but that's okay. Okay, that's the whole point of this particular program. Breakpoint on line 7, run the program. You cannot do the trick unless you're in execution of the program, because the variable d is a local variable, so it doesn't even exist until main is called, and that's why you cannot really access d unless the program is actually executing. So the way we do it is we say d is 0x c88 0 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There we go. Bad breakpoint. Oh, set var d. There we go. Okay. So then we can say, print dereference, but this time we want to do the reverse. We want to look at the address of d as the address of a double, and then dereference the pointer. And that turns out to be this number. How do we know that is 2 to the power of what? 137? Well, I think it's definitely in the right ballpark, okay? But if you really want to confirm that, we can quickly do that part, because we have this already opened. I'm going to use a spreadsheet to do the calculation. So now we can just say equal power 2 to the power 2 to the power 137, and right there 1.74225 times 10 to the power 41, and then we double check this one. Yep, well, we just got more precision here. In other words, I just verified that my answer is correct. Is that okay? What about the other way around? If I give you a particular value to represent, can you reverse the process and figure out the double representation? Well, that's actually your homework, right? But you cannot run your program during the exam. I'm not going to give you guys something that is really, really awful and difficult to deal with. Something that's easy, like the value of 5. Okay? So I'm going to put it into the practice exam tab here. Okay. So this is another question. This is question number 8. So we'll make this number 9. Okay. How do we represent the value of 5 as a double? Specify the bit pattern and show your steps. Okay. How do we do it? How is your program going to get this accomplished? So you start with, it's 5 times 10 to the power of 0. Remember this? This is where your program starts. And then what do? We want to get rid of the power of 10. We want the power of 10 to be 0. But guess what? It is 0 already. Oh, okay. So now you say, okay, now we have a bit pattern of 0101 times 2 to the power of 0. 0101 is just the binary version of 5. Is that okay? But 0101 is not exactly in the format that we want. Now for this one, if you want to go through the same logic that we specified for the general calculation, that works. But there's a better way, there's an easier way to do this. Okay? So the easy way to do this is to look at this and go like, oh, but there's an implicit point here. Okay? Can we buy that, we can put that point here and not really change the value of the representation? Okay? All right. So what about this? Can we somehow change it so that it becomes 10.1 in base 2? If that is the case, do we need to change the exponent of 2 to compensate for moving the decimal point or binary point in this case to the left by 1 digit? And if so, how do we compensate for that? Well, it's either 1 or -1. It's going to be 1, okay? Because when you look at this value, 101, it is twice the value of 10.1. Is that okay? All right. So we need to compensate by adding 1 to the exponent of 2. Okay, the next step is to write it like this, shift it one more time, and how do we compensate that as a power of 2? Becomes 2. Okay, very good. And I claim that we are really close to the answer now. Okay, what is the sign of 5? The sign B is a 0 because it is not negative. Is that okay? What about the mantissa? Or the fractional part of it? It is 0, 1, and then a whole bunch of zeros. Right? Because we are only looking at the digits to the right-hand side of the binary point. The 1 point is going to be implicit. It's never represented explicitly. Okay, so the only tricky part is E. Now, we know that the actual exponent of 2, which is 2, is going to be E minus 1023. So that's going to make E what? 2 plus 1023, and that turns out to be 1025. So now the question is, okay, how do we represent 1025? We know we have 11 bits to do this. Okay, so let's count all the bits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, we know 1024 is 2 to the power of 10. So that means there's a 1 here. That takes care of 1024 with only 1 left. So which bit should I turn on to represent that one last quantity of 1? There you go. So now we have all the components. So when you string the whole thing together, the sign is a 0, and then you have 1, 0, 0 coming from here, followed by these 4 zeros. And then after that, you have these 4 zeros over here. And then we have the mantissa, okay? Because so far we have taken care of the sign, which is the most significant bit. This is bit 63. This is bit 62 down to bit 52. And now we have the fractional mantissa, which is this bunch here. And we break it up in groups of 4. Say that one more time. There will be 12 groups of 4. 13. Yeah, 13, that's right. Yep, there will be 13 because 52 divided by 4 is 13. That's right. Okay. The Bluetooth, when this operates in Bluetooth, I can actually turn on the external mics so I can actually hear you guys better than with my own ears. But when it's tethered by Bluetooth, for some reason, it cannot get into that mode. Because when I double tap, it doesn't, open up the external mics. I turned off noise canceling already, otherwise I wouldn't be able to hear a single thing. Let me try that. You guys go ahead and try to talk. It's very comfortable. It's all quiet here. I can't even hear my own voice, which is really weird. All right, so now we have this bunch of digits. How do we convert this from binary back to hexadecimal? Look up that table, okay? Group, because it's already in groups of 4. So we look at this group here. 0, 1, 0, 0 is 4. The next group is a 0. Okay, this group is a 0. The next group is a 1. The next group is a 4. And then we just have a whole bunch of zeros after that. Is that okay? Yep.
Well, don't you have to make the first one a C because you have to account for the 0 for the sign bit?
But the sign is a 0.
Right. But if the sign's 0, but that's still a bit.
It is. And that's why we have this one here.
Yeah, so I'm saying that you wouldn't put 4, you would put C to represent 0, 1, 0, 0.
No, you would have, but 0, 1, 0, 0 is 4.
Oh, right. Okay. Yeah, you're right. Sorry.
Okay.
Gotcha. Because it was negative.
Yeah, because the previous one has a negative value, so the sign bit is a 1, and that's why we have the most significant bit being a 1. Okay, so it's time to test it. So we go back to the GDB, which is still here. Okay, we'll say set var d equals to 0x4014, and then we have 12 zeros here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Press the enter key, and then print it again, and it's just 5. Now now using this technique, you can actually play with various values pretty easily. So you can do it the other way around too. You can say set var, and then do it like this here. You can reverse the whole process. You can say I want to represent 127. Tell me what D looks like. You can do it like that too. So this is a really good tool to help you do the homework. Okay, how many people know that you have a homework? If you went to the lab on Tuesday you would know. But I still haven't written up the actual homework assignment yet. So I I will assign it today, and then you have 1 week to work on it, so that it'll be due on the same day as the exam, which is not a bad thing because it will keep your mind fresh, on how to do double conversion and all kinds of stuff like that.
So I'm assuming the homework is just the last assignment plus now show it as a
Yes, there is a file already posted on in this module. So if you go to the same module where you find addition, subtraction, and stuff like that, there is this particular program, and this is the starting point for you. I have not written out the actual homework description yet, but this is your homework basically already kind of explained here. So the only difference compared to the previous one is we have this extra convert to double, subroutine that you are going to write, so that you are going to return the 64-bit representation of a double as a 64-bit integer, just like what I did in class today. So you're going to have to specify your own logic here. The rest of the program is already done. In other words, I am giving you my parser. So if your parser is not working or it's not working 100%, don't worry. You can just use mine, okay? And then by the time, okay, if you look at main in here, main is going to call parse cis310 just like in your previous homework assignment, except depending on the structure P, we are also going to use it to call convert to double, which is the subroutine that you have to implement for this particular homework assignment. Is that okay? Does everybody understand what you have to do in this case? And then the restrictions, which will be spelled out also when I actually type the homework assignment description. So the restriction is you cannot use casting into doubles. I don't want to see the word double other than in comments. I don't want to see the type double used anywhere in this program. He's laughing because he's thinking, hey, if I can use the double type and I can use casting, I can use one single statement and get the whole thing done. I don't even need a sentence. I just need return, and then it's substituted with a long expression, and the whole assignment is done. So no, I don't want to see the use of the type double anywhere within this program, or the calling of any library subroutine that will give you a double. So no power, no exponent, no log, okay? So you have to do it the same way as we talked about it in class. Is that okay? So that's due next Thursday because most of you did not know about it, so I'll give you 2 extra days to do it. But the earlier you do it, you're actually helping yourself study for the test. So I would say that, hey, if you get it done early, good, okay? But get started early because it is a part of your studying. So are there any questions about the practice test? Because I think this is going to conclude the actual practice test. So there will be questions on doubles. Yes? This line? Okay, so what we're moving is we're moving the binary point to the left by 1. Okay? If this is base 10, would you be convinced that I need to multiply by 10 in order to preserve the value represented by the entire expression? But we multiply by 10 only because it's base 10. In base 2, we multiply by 2 because the base is 2. Is that okay? All right. Any other questions about the practice test?
When you're moving the decimal point, you could think of it multiplying by a 10 to a negative power and getting rid of that power.
That's one way to look at it. Okay, but there's a graphical way to look at it as well. So the graphical way to look at it is basically you have your point here. I don't really care what base you're dealing with. Okay, so I'm just going to use some space placeholders here to represent the digits. Okay, this place is telling me. So let's assume that B is the base that we are using. This is really just specifying how many B to the power of 0 do we have, right? This one here is telling us this is multiplication. How many B to the power of 1s do we have? How many B to the power of 2s do we have? How many B to the third power do we have? But on the other side, this is B to the power of -1, B to the power of -2, B to the power of -3, B to the power of -4, and so on. So when you shift the point, you are really just either multiplying the entire number by B or you're dividing the entire number by B. Is that making sense? Sort of? Okay. So in order to preserve the value after we shift the point, then you have to adjust it with B to the power of some kind of adjustment here so that we can preserve the value that is being represented. Is that making any sense? Sort of? Okay. If you move the point from here to here, that means what used to represent the quantity of power B to the power of 0 is now representing the quantity of B to the power of -1. So the whole value is now divided by B. So if you do it like this, this will trigger an increment of the exponent adjustment. Yeah, is that making any sense? All right. Cool. All right. So if there are no further questions about the practice test, the next thing we're going to work on is to go back to the memory devices because there were a few questions, a few really good questions asked this morning about the memory devices, and it is from the big picture perspective, like what is this doing? Why do we need this when we already have that, and so on. So for that discussion, I'm going to switch the notes to the memory module so that we have a way to refer to the various designs. So we start with the SR latch, okay? And let me use a picture here to represent the SR latch. So the SR latch is a fairly simple design. Okay? Usually it's represented as a box. We have /S/R, we have Q, and /Q. Okay, yep.
Last time we were about to reach a registry.
I think we kind of rushed and talk about registers, right? Yeah, but it's still good to kind of revisit the topics from before. We only have 5 minutes left, so we are not going to have a whole lot of time to finish that discussion. But it is good to look at this first. So with a latch, what you're doing is if you have 1 1, okay, /S/R 1 1, okay, the meaning of this is to maintain state. This is why a latch is also the smallest and the most rudimentary type of memory device, because when the input is 1 1, you're just saying, okay, whatever Q was before, keep it the same way. Whatever /Q was, keep it the same way. It's maintaining the state of the latch. When you have 0 1 as input, then you're asserting set in this case, because it's active low, and that's why you see a slash before the letter. So in this case, you're setting the latch, which means Q will become 1 if it wasn't 1 before. Is that okay? So this one is for setting the latch. If you have 1 0 as input, /S is a 1, /R is a 0, that means you're resetting the latch. Resetting the latch means Q is going to become 0. And the only really troublesome state is 0 0, because when you specify 0 0, you are both setting and resetting the latch. This is the only time when both outputs Q and slash Q are going to be ones. Is that okay so far? Okay. So typically what you do is you either transition from set to maintain, or you transition from reset to maintain, so that the output is either a 1 for Q, a 0 for slash Q, or opposite, which is a 0 for Q and a 1 for slash Q. The troublesome transition is from 0, 0 to 1 to 1, 1. That will cause oscillation because you have a simultaneous transition, but because the gates built into the latch, they're not simultaneous devices. So each one will take some amount of time from the moment of sampling the input to changing the output. There's a certain latency, and that latency is going to be 1/2 of the cycle time of the oscillation. Okay, so this one is bad. Okay, you don't want to do a straight transition from 0, 0 to 1, 1. So if you're from 0, 0, you want to go through one of these two before you transition to 1, 1. So that's the idea. This state by itself is not problematic. It is the transition from 0, 0 to 1, 1 directly that is a problem. So in order to go from 0, 0, you have to go through either 1, 0 as input or 0, 1 as input before you transition to 1, 1. That will be okay. Is that okay? So even though this is a memory device, it is not easy to use. In other words, if I say, okay, this is the sum of some calculation, okay, I want to store it. Let's say it's a 4-bit number. How do you store the sum as a 4-bit number using 4 SR latches? You can't, okay? There's just no way to do it because each SR latch is only allowing you to specify one pin specifies, do you want to set? The other pin says, do you want to reset? It's not convenient. So when you look at a D flip-flop, this is a gated D flip-flop. It has a D and an EN. The D port, which is an input port, specifies, do you want to change to a 0 or do you want to change to a 1? So D being a 1 means let's switch the output to a 1. D being 0 means let's switch the output to a 0. Ah, that is handy, okay? Because now you have one single input pin to specify the bit value that you want to store. EN is called the enable. It is also it's what is enabling the device to update. When EN is 0, you can do whatever you want with D, and it's not going to change the state of the flip-flop. When EN is a 1, whatever you specify as D will become Q after some latency. Is that okay? So that means you can, in fact, use several of these things to make a multi-bit storage device. And the cool part is you can tie all the enables together. Okay, so this is one enable pin from outside somewhere. This becomes D0, D1, D2, and D2, D3 here. So these data bits can now go to the result of an adder. So now we can store the result of an addition quite easily using only 5 pins, 5 control lines, or 1 control line and 4 data lines. Is that okay? Okay. So if that is already doing the job that we think a flip-flop should do, why do we have something that looks like this? There's a D, but this time we have a CLK or the clock line, and here's Q. So this is a edge-sensitive D flip-flop where it will only change Q to become D when CLK has a transition from 0 to 1. Okay. So that means if your D is doing some crazy stuff like this, okay, but your CLK, this is D, and your CLK, your clock line, is having a transition right here, okay, like that, it's going to store a 0 and ignore everything else. Because only during this transition that it will sample whatever D has and then change Q to reflect that. All the other time, every time, all the time over here and all the time over here, it's not paying attention. Okay? So a edge sensitive D flip-flop allows you to specify a very narrow window to update the state of the flip-flop, which is good. Because when you look at an adder, how long is that output from the adder is going to remain valid? Well, maybe this much, maybe this much time. It depends on a lot of factors. But if you can guarantee within this narrow band of time, the output of the adder is valid, and you can somehow schedule the clock to clock during that time, then you know for sure that you're going to capture the correct data. On the other hand, if you have okay, let's go back to the previous slide here. So on the other hand, if you have a gated D flip-flop, okay, and your signal goes like this, okay, so you have D here, and then this time you have EN, and let's say you go EN like this, okay, turns on for a little bit of time and then turns off, okay, and then D, okay, is going to do some transition here because that's when you present new data to the adder, and you have something that looks like this. So in a timing diagram, this kind of thing basically means there's a transition here and there's a transition here. But you can see that there's a certain margin here. In other words, that is the gap of time where we're not really quite certain about the validity of the adder. Okay, maybe it's right, maybe it's wrong, but it's in transition. Unfortunately, your enable line is also having a falling edge at this point, which means the last moment, the last bit of data that you're capturing may or may not be valid. So that's why the enable method is not always the best way to do things, because because during this time, it is updating all the time. During this time here, your D flip-flop is updating all the time. However, your data line is changing, it will change the flip-flop itself. On the other hand, if your data looks like this, if you have a clock, okay, if you have a clock that has a rising edge right in the middle of the point where the data is valid, then you're going to capture that one single moment for sure and ignore the transitions at the beginning and also the transition at the end. So that's why the edge sensitive flip-flop is going to be useful in this case, because it can control the timing of the update. Yep.
What if the clock starts the rising edge right when data is being changed?
What if the clock, that would not be good either. So if you move it here, that would not be good because it will coincide with the data just being in transition. If you move it over here, it's not good either because that's also a transition. Okay. But the clock is useful because the entire computer system, including the processor, shares a quote-unquote global clock. So everybody basically walks synchronized using that drum, using the beat of that drum. So so it's easy to synchronize devices to do things quote-unquote at the same time, and it's easy to control timing that way as well. So that's why the clock signal is really important. It doesn't seem important at this point because we only have looked at a D flip-flop all by itself without all the other things that connect to it. Okay, so the value of a clocked signal or the clocked flip-flop will become kind of evident when we talk about how a register fit inside an entire processor and how it fits in with the adder, the subtractor, the ALU, and everything else. But the key point here is the rising clock property allows us to limit the update time to a very, very small amount of time instead of being something that is spread out like that. Okay, so we are running out of time. I'm going to stop the streaming. And when we go to the lab, you guys can work on the new homework assignment, or if you have any questions to ask about floating point numbers or the practice test, that would be a good time to ask as well.